Okay. So yeah, yeah, I was talking with the Ilya for the okay. So I'm sorry, there is oh my God. Yeah. Oh, sure. The Mac doesn't have the I'm sorry. Okay, just I'm going to rejoin to share the screen. Sorry about that.
So while we are waiting for Minchang, Ilya, do you want to get started on just the context and background, and then when he joins? Okay, he's joining. Okay.
Okay, sorry about that. Yep.
Yeah, go ahead.
Yep. Okay. So let me share the screen. Yep. Yeah. So okay. Good to see everyone. So my name is Minjang. So I am from the Meta. So so we were talking with the so we were working on some the basic boilerplate code and the initial work for the Triton CPU. So today so I and Ilya will represent our current status. So this is a few background. So let's just start with the motivations. The motivation is it was actually pretty straightforward. So CPU was a kind of the missing part in the Triton ecosystem, and I think that both internally from our Meta and in general open source community. So we wanna I mean looking for more heterogeneity. So that means that we wanna support more on the CPUs. I mean, including Intel, the ARMs, and also there is a lot of demand from the Apple silicons, including metal for the GPU side. And yeah, and it's not surprising that some workloads are really better on the GPUs. For example, I mean, the small batch sizes and some latency important, the inferences are usually better on CPUs. So yeah, so and we also have our internal needs. So for example, so we do have our internal the Jupyter notebooks. So many people and the data scientists are working using these notebooks, and they are using the PyTorch, and we encourage using the Triton over the CUDA. So yeah, the supporting CPU backend for the Triton will be really great for the entire community. And we were talking. The Ilya and I were talking. What is the success criteria? So at this time, at least we don't have the very strict the goal, but these are just one of the example. From the Intel was thinking so one DNA kernel, the API performance on CPU may be similar to or the reach certain percentage of the GPU or the other counterparts. So there is this will be one of the good example, the perf goal. From our Meta, at this time we didn't set a goal for the performance itself, but instead, so we are thinking at this time the coverage and the developer's experience are more important right now. So for example, if the most of the Triton kernels can be run on GPU without major source code changes, I think this is also great success for us. But but this can be discussed further. So at least from our meta, so we are dedicated to invest 2 full-time engineers, and we will onboard 1 PhD intern during the summer. He will work for 12 weeks, and at this time, so we were thinking the project could be supporting ARM Neon vector operations. So at least we like a 2.25 engineers per year. So that is our commitment right now. And we hosted our the Triton CPU, the repo under the PyTorch labs. So so I just started some basic plumbing, and Ilya did some his also sketch in his own repo, and we will coordinate how we merge those to work right now. Both of them are at this time it's early stages, so I don't think this is a big deal to merge of them. So I want to briefly discuss the basic, the dialect and the transformation for the CPU backend. So left side is what we have right now. As we all know that the basic the big the translation, the tree is that TTIR to the TTGIR, and it goes to LLVM-IR eventually. And then we have also the transformation, the table gen, the Triton to Triton GPU, and the Triton GPU to the LLVM. But interestingly, for the GPU side, we also have NVIDIA specific, also the AMD specific the dialects or the transformations. So currently we do have like a Triton NVIDIA GPU to LLVM. Also for AMD, we have corresponding Triton AMD GPU to LLVM. There is also MLIR, the NV GPU, MLIR already there. So there is also the NV GPU to LLVM. So those are 3 or the 4 transformations are the working to lower the TTIR to eventually LLVM-IR. So at the very first time, so I was trying to match the GPU word to the CPU word. So this is initial sketch, and this is not that surprising. This is a pretty obvious the mapping, right? So we will have the TTCIR, and we will going to have 2 important transformations: Triton to Triton CPU, and the Triton CPU to LLVM. So that will be the I think both in the I and the Ilya are thinking this is the initial approach. But I do have some I mean at this moment this is not a big deal. But the one thing I really don't it's kind of a weird one is that the CPU right now is in the third-party directory. So at this moment, the implementing CPU backend, just like NVIDIA, AMD is mostly straightforward. So right now, the CPU is added like third party the backend, just like NVIDIA and the AMD. But it looks like it might be better if we promote CPU to the general the backend support. Then we can have more specialized the CPU support in the third party, like a Triton AVX or the Triton Neon, CPU to LLVM. So, but again, so this is not the urgent issues. And once we have some decent amount of the work, then we can consider this kind of the refactoring. And one of the reasons is that the meta, we also want to support the Neon the vector operations for the mobile devices. So in this case, yes, obviously the CPU backend should be used by both AVX for the general, the Intel or the AMD CPUs or the ARM CPUs. So in this case, at a certain point, it'll be better to redesign this one. So so this is the quick the table how we match the GPU to CPU word, and some of them are in the general tree. Some of them are third party. So this is my initial thought, and Ilya will discuss his initial work, where he did the convert the tt.load to the vector.load with the vectorization. So Ilya, can you take it?
Yeah, thank you, Minjan. So
Yep.
on our previous Triton CPU meetings, we discussed like which dialects we can use to help in our lowering, and one of our obvious choices was a vector dialect, because we want to produce vectorized code, and vector dialect provide us nice abstractions on a multi-dimensional vector that is target independent and that can be lowered into different architectures, including AVIX and Neon. And for many Triton operations, we have direct mapping, like for element-wise operations, scans, reductions, but it wasn't clear what to do with memory accesses, how they actually map. Can we express them through vector dialect, including our features for masking and boundary checks? So I made some experiments on that on my prototype, and actually for memory access we can like split them into few categories. So the first one is threaded access. It's actually the most common and the most important case, but it's explicit only when we use block pointers. In other cases, we need some additional data flow analysis to detect those patterns. And for now, we assume that Triton CPU will be able to do it in most cases, at least. So we expect this case to be translated into vector load stores, probably masked. For some strides, it can be transformed into gathers and scattered. So another case is when we have indexed access. Those are cases when we have no information about indices. For example, we lower them from memory, what happens in touch operations like index select, index put, and those should be translated into gathers and scatters as well. And the most generic case is when we just have a tensor of pointers we have no knowledge about. I don't think we actually have some kernels where we load pointers from memory, but should consider this case as a fallback when our data analysis fails. So in this case, we just fall back to scalar loads and stores. And my experiment was about the most important case with threaded accesses. So could you please move to the next slide? So vector dialect has transfer read and transfer write operations, and those operations actually cover all our needs with load accesses. So it supports strided memory access, it supports indices, masks, and even bounce check. So we can actually directly transfer Triton loads and store into transfer read and transfer write, and all we need to extract memory reference, because vector dialect works on memrefs and indices. So block pointer in Triton is actually a combination of those two things. It has base, it has offsets, sizes, writes. So what I did, I introduced Triton CPU operations to extract basic memref from block pointers and indices, and I used those to build transfer read and transfer write operations. And on the next slide, it's shown the result, and I could transfer Triton load with boundary check and transfer read, and it actually produces a nice, clear, and working AVX 512 code that does exactly what we need. So I think that clearly demonstrates that it can be used to efficiently transfer loads and stores with boundary checks and masking. And I think it's a good way to go at least for now, because it can save us a lot of time compared to direct translation from Triton to LLVM-IR. So for now, I think vector dialect can be used to significantly speed up our work on CPU prototype, can easily map most of operations into vector dialect, and get a nice vectorized tool in LLVM. And that's it from my side. For now, it's all in my private branch, but we started merging process, and I hope everything will be available in our public repo. Thanks.
Yep. Thank you. Yeah. So so we also, I mean, we and the Meta engineers, we also internally discussed what is the another approach, those to generate the LLVM code. So we might also try to directly generate the vectorized code. So for example, a tt.load with the access info, the contiguous information. So maybe we can directly convert it to the AVX512 in a loop if the block size, the number of elements are larger than the vector width. Then also we can do, I mean, lower to the ARM neon. So yeah, clearly there is a pros and cons, but it might be worth it to try this approach as well. And we are also thinking that if the new proposed linear memory layout can be good for the CPU as well. Yeah, but anyhow, this is the work in process from our side. And yeah, the loop fusion is also super important topic, but today it's I mean, we don't have much time to discuss this one, but so we can discuss later in the separate Triton CPU meeting. So yeah, but that's the all we have today.
Are there any questions or comments for Minjang and team?
Just one question for Ilya, actually. So then you're talking about how you can use the vector dialect for cases where we have block pointers. So for cases where there aren't block pointers, then you're gonna convert the loads to scalar operation, and for that you're just gonna have to go through the LLVM dialect translation.
Well,
That's
the
plan.
basic idea is that on a translation from Triton to Triton CPU, we analyze memory access patterns, and in most cases, we actually have loss from tensor of pointers, but in fact, it's a strided access. So we can translate them into block pointers. So example was about block pointers, but you can think that when we have any strided access, we transform it into block pointers or directly into transfer read. And after that, Triton load is used only in those cases when we don't have enough information to vectorize it. So in these cases, it will go into scalar loads.
Okay.
Can I say that I will say, sorry, this is Justin from OpenAI. I will say that one of the design criteria of Triton is that at least on the GPU, and you probably want this on the CPU, or I'll say we probably want this for any CPU backend that will accept, is that we don't rely on sort of very fiddly compiler optimizations in order to get good performance. Because I think we've all worked on compilers like that, where it's really hard for users to write high performant code because they, write something and it works, and then they change, they add +0, and then all of a sudden the compiler can't analyze it or something. So I'll say, at least for my part, that in terms of something that we would want to accept upstream as like an official backend, it should have that same property as opposed to relying on fiddly optimizations.
I mean, I think the analysis of pointers is kind of needed for CPU, as there's no gather, right? So some of it
gather operation in AVX512, isn't there?
Sure. I mean, there's no efficient gather in general. There's no. I guess it's not the way you would want to write efficient code in general.
That's definitely true, but we definitely want to have a guarantee that to users that either it's going through the efficient thing, if it can be efficient at all, or it's going through the most efficient alternative, which would be a gather, right? And it sounds like in the current design, we can't guarantee that because it's a best effort analysis.
Yeah, I agree. And I'm also, I don't know, for having worked on it, I'm a little concerned about like the memref usage and all these things that I think they come with a lot of baggage. And yeah, I do wonder if that's the best representation, but I haven't followed enough the discussion to say that my opinion is right.
Ian, go ahead.
Thanks. So I was curious. So we talked previously about the. I know it's a pet project of mine, but the Triton shared project, and I'm curious if you're able to reuse any of the pointer analysis that package provides. So a lot of this is a solved problem there.
So far, I personally didn't any work on pointer analysis. So my experiments was on block pointers directly expressed in Triton. So other cases would like have to be mapped to it. So no pointer analysis is in prototype yet. And we wanted to look first into the access info analysis that currently is in Triton.
Sorry, I'm just going to like interrupt there because it's related. But by the way, there is also an analysis in Triton for like pointer continuity and stuff. I don't know if you got a chance to try it again, and if you can comment maybe on the difference between what you have and that.
Yeah, so there's some similar roots in the two of them. We went over the access and info analysis when we first started developing Triton Shared. I'm not sure if progress has been made to sort of augment that or change it, but we found that it wasn't sufficient in finding the contiguous blocks of loads and stores that we needed for what we were doing. So the analysis is sort of specialized to look at the strided memory loads and find contiguous chains, and it combines sort of the mask analysis and the pointer analysis.
Oh, is there a fundamental kind of difference in the algorithm, or is it just it's missing cases?
I think it's just we're looking at different aspects of the IR and just tracking different things. So,
fair enough.
It's been a year or so, so I don't remember exactly what the differences were.
So I have a question. First, from meta side, so you said your interest is mainly to make Triton code work on the CPU. Performance is second consideration for you. You're talking about existing Triton code writer for GPU, or you are talking more like people just encourage them using Triton, the new code for CPU. And I was mainly thinking this broker pointer thing. So like existing code that maybe using non-broker pointer, or you have a chance to influence them to use broker pointer so that it make it easier to map to CPU.
Yeah, I may be a bit more, take my word. So the perf is also pretty important, but we didn't set a strict goal right now. But so this time, the improving the coverage and the dev experience is more important. But yeah, I'm not a super expert in the how much the Triton kernel we have right now. So maybe if there is another the meta engineers here, so maybe they can chime in. But yeah, so but at this time, so we want to.
Yeah, Minjiang, I suppose I can comment on that. This is Lee. I'm Minjiang's manager. So I think that the reason that more coverage and heterogeneity is important is that at least we can encourage people to be writing Triton code. They don't have to feel they have to write custom CPU code, and that means we can port the code and have the flexibility. And of course, we can always then tune that Triton code. We can encourage best practices. We can do custom CPU paths if necessary to be peak performance. But it's a a longer term concern at that point. Like we need to get to the point where we can port the code and just write Triton, and at least if we really need to migrate and it will just work, and then we can focus on performance. So that's why the priorities are that way around, and why like full coverage would be a more important goal, so that everything just works, and then performance we can deal with as necessary later.
Yeah, I see.
Yeah.
My point is that if you are more like at early stage, you have a chance to encourage people to write using a block pointer, which is much more friendly to CPU.
Yes, I agree. Yeah. And we'll push for best practices for all of this, of course, but the same applies to the GPU code. And so we'll work with that over time.
And then
I want to encourage, go ahead.
So I have another question, actually, to the OpenAI side. So we know that the Triton was created to get a really good performance, but also have a very good user ease of use part. The criteria for CPU, would you consider the same, or you would relax it a bit so that just help Triton be broadly accepted? Because people may not as care that much as they care on the GPU side, given the power of computer power is relatively smaller than GPU, but they still enjoy that, like the ease of programming side. I think that's like related to the criteria, like how you accept these things to official tree.
Yeah, again, this is really a question for Phil, but my feeling is that we need to have a path towards getting good performance for something that's sort of in the official Triton repository. And part of the reason is that if it's in part of the official repository, people are going to expect us to have good performance. They will benchmark us. They will also file bugs, and all of that's overhead for the OpenAI folks. So obviously version 1 doesn't have to have good performance, but that was sort of to what I was saying earlier, that we need to have a path towards something that is tunable so that you can get good performance, as opposed to just saying, like, because if we don't care about performance, just run the interpreter. If you just want to play around with Triton, the interpreter is fine. It's very, very slow and will never be fast. But that's your way to just play around with Triton without a GPU.
Makes sense. Yeah. Yeah, but you know, it's this is difference between like a 1,000 slower than just like a 50% versus 80% of peak.
Actually, if you could clarify a little bit what you mean by simplicity, like, are you saying that if we take, like, for instance, some of the kernels we have for GPU, you would expect them to run out of the box on CPU? That's what you meant by simplicity, I'm guessing. And that's kind of related to what we had discussed on Slack about, oh, should Triton do tiling and things like that, or is it something separate?
So for me, it's something separate. It's not really to that deep level. It's just that people using the same language so that they can apply to the other architecture. That itself has a value, I think. That's what I'm hearing from Meta.
Right. I think there's no plan to change the language, right? That would stay. And I don't think we have a reason so far. It's obvious that there are some use cases that are going to be working well on GPU and not on CPU. Like, for instance, like we discussed, gather and things like that are not going to be as efficient on CPU. But the language should be portable, and and generally you shouldn't be 1,000 times off for like because you're doing a gather rather than a block load.
I think one of the design criteria for Triton 2 is that we actually don't think that it's a language that people should be using for its own sake. Like, encouraging more people to use Triton actually isn't something that at OpenAI we're excited about. Encouraging, building a tool that's useful for people, awesome. And if it can be useful for people on CPU, great. But if the only benefit from something is it makes it sort of encourages more people to use Triton, but doesn't actually help any real use cases, actually, I would say that that's not something that's interesting to us.
Okay. Thanks, Minjang and Ilya. Let's move on to the next topic in the interest of time. So, Jianhui, do you want to introduce the second item?
So sorry.
It's the layout design related one.
Oh, okay. Yeah, I think that there are some mentioning that Phil was saying, like, you guys were gonna to work on some new layout design. Then I saw this linear layout PR. So that was when Phil said that was in the Triton CPU design background. So contest, then I was wondering that when you design this linear layout, is that the layout mean for Triton CPU also? I just want to get some.
You should be able to use it for Triton CPU. Yeah, should be fine. So for example, like you can model vector registers instead of linear layouts. No problem.
Okay, sounds good.
Okay, and then we have the AMD team to discuss Triton Stream-K. Jason, do you want to get started?
Yeah. Yeah. Hey guys. It's actually Xiaohu from our team is going to present this topic. So yeah, thanks Xiaohu for putting this together. Thanks everybody for the attention.
You share my slides. Okay.
Yeah, we can see it.
Right, you can see it now. Okay. Oh, I need to switch. Yes. Can you see it now?
Yeah, we can see it.
Right, yes. Great. Thanks. My name is Xiaohu. I'm working from UK. So so today I'm going to talk about Stream-K developments in AMD in Triton. So I have a few sections. So first I want to mention why is Stream-K. To start with, I want to just give you a quick review about classic data parallel gem. So there's few things is for matrix C equal to A times B, and the parallelism actually coming from the output tiles. So the tiles basically we decompose the output matrix C into number of independent chunks, which we call tile, with size with block M times block N. And that's the one. And within each tile, the calculation is completely independent with other tiles. And the second thing is we have, depending on the size of K and block K, we can calculate the number of iterations within this K loop, which we normally do what we call matrix accumulation loop. So basically, with the block K, block N, and block M, block N, and block K, we basically have be able to calculate the total work loss across the whole gem. So that's a basic data parallel. The issue normally comes with the size M and K plus all the block size we choose. We know the performance all dependent on this block size we are choosing on various type of GPUs. If you are lucky, you decompose your matrix with this 2D kind of a tile, and you can evenly distribute across a number of computer units in AMD or in CUDA term we call the SMs. You can evenly divide it that, then the life is easy. And however, in most real applications, because of this, for example, here I have 9 tile, and I have 4 SMs, and within each, with the third way, we can see there's a resource basically unused. So, and with this, general people, what they do is, if you want to increase the usage of the resource, what you could do is basically, let's say, half of the size of the tile size. Then you can improve the improve from like 75% to the 90%. However, there always this kind of gap. So the first question basically is, can we actually implement a new scheme so that we can actually resolve this resource unused issues? Another kind of questions coming up is, for those problems with very large size of K, can we further actually parallelizing K domain so that we can get more parallelism if Mn is very small? So then there's, then I guess most of them, you probably already heard the split K already in the Triton. So, but the problem is, for the split K is depending on your how many of K you're going to split. There's always, so I have some summary here, is basically there are always some of kind of scratch workspace basically for, because of a K split, there's partial sum around for each working group. And if you use atomics, there's also partial workspace you need to allocate it. And this is not constant size, it's depending on the number of K you're going to split. So that's the one of issue we want to also trying to deal with. Can we actually have a constant scratch workspace for, because of this K, a large K you have to split across the working groups? Another thing is this also further complicated the auto-tune and kernel selection for, I guess for most of us, if we develop libraries, this is always going to be the key issue, most of the computational intensive part actually. So yeah, so that's the basic motivation we want. So we want basically, can we have the generalized load balanced approach to deal with the above issues? Right. So just to roughly give you how we actually deal with in the Stream-K. So assuming we have like 4 CUs or in CUDA term, we call it 4 SMs. We can launch so idea is we want to launch a constant number of work groups per CU. And second thing is, we know the total workloads. This total workload is about like number of the total tiles times each tile have a constant number of iterations because of a K loop. So so we can actually give each working group an even share of the total iterations of this matrix accumulation loop. And because depending on the size of M and K and the tile size of and the tile size and also block size of K, we sometimes most time you might come across a situation is one tile will be shared by different CUs. So and to do this, we need kind of basically fix up this accumulation for example the number 2 tiles, number 6 tiles, and number 4 tiles. So so that's the basic 3 things that covered by the Stream-K, and from this we can see we basically can do the job basically evenly load balanced share across the whole workloads, no matter how many CUs or how many SMs you have on one GPU card. So GPU devices. So that's also give you naturally give you a next questions, is because this one we basically open up all the K loop. Can we and this is this the main kind of implementation, or can we come up some even another alternative to implement this? But the basic idea of Stream-K is here. So in our Triton implementation, we actually consider 2 things. First thing is we can calculate the whole decomposition with this 2D loop. And we also can do is in the first part, we want to make sure all the reminders we can actually distribute in the first wave, and then the rest of in the rest of the work will be all the tiles will be divisible by number of SMs. So and so the second one will be called full tiles. So this naturally gives us, can we actually use two kernel approach to do that? And in the later, I also want to say we don't have to actually use, although we have this decomposition, we don't have actually divided, we don't have actually to use two kernel approach to implement this. Even we have this such kind of similar decomposition. And I think I forgot one slide, but I think one thing is we can put the first wave in the front, and we can put the full tiles in the second. And we can also switch around using full tiles and at first, and the first wave in the second. And in my experiment, I found actually first full tile is put into first. We actually get a better performance, which about like 10 teraflops difference, I think, depending on your size, I guess. Right. So the next part I will be try to give some Triton implementation status and initial performance evaluation. So in the Triton, we have quite a few versions of the implementation. For example, I've just mentioned about two kernels, which is first wave and full tiles, and then we're trying to merge these two kernels together. But merging is also different ways. We can use if else to distinguish the work in first wave and full tile. Or if we don't want to use atomics, we can, because of this atomic, to replace atomic, we have to do some partial sums. So we use one extra kernel to do the partial summations. We also do the working in progress for single kernel with or without atomics at the moment. That's the current summary. And one thing I want to show here in this is VGPR vector general purpose register usage. You can see we have a tuned gem and also Stream-K. From the register count and also spill count, there's no much difference. And also pretty much the register usage is pretty much decided by the tile size. And also, I think you can notice that Stream-K has a larger spill count, just a larger usage just because of algorithm complexity. And also, you can see that there is a descent speed up compared with PyTorch native matrix multiply. Another thing is I want to also show something about number of warps here. You can see VGPR count will be affected by the number of warps you can usage. Number of VGPR usage is actually affected by the number of warps. I think this is actually related to trying to relate to the occupancy. So that occupancy give we need to actually, so this is a graph I really want to show is there's necessary actually to for the tuning part. Well, I only showed one parameters. We have quite a few other parameters also can be taken into the consideration, which I'm not sure quite the whole view of numbers here, but this is just one number. Just want to show you what could be affected in or some kind of like or some future work we really need to work on. I also want to try to see the difference about tile size effects about the performance. So I only tried like 64 by 64 by 64 and 128 to 64. You can see there's a few spots around middle-sized areas. When you use the larger tiles, the benefit. I think this is all you observe from here. But I forgot to mention that is we have 1,000. This graph is basically generated by our 1,000 points of different size of matrices, and by just using like one tile size, I think we already observed the speed up versus with standard PyTorch Matmore, and that also give you the idea is when we do the auto tuning, we might, we still get better performance, but if you do the tuning, but in terms of number of size of tile we need to tune, maybe much more smaller than generally other kind of approach. And we have some observation as well. So yeah. So this is the current Stream-K implementation for all performance profile. We have few size which is below the speed of 1, but for the bit larger size is not ideal. So we need probably working on this quite a bit in the future. But for the other smaller size, it seems quite decent ones there. I also compared Stream-K implementation versus Triton Matmore implementations. I only use like 64 by 64 by 64, whereas the Triton Matmore tutorial, there's a limited amount of auto tuning there, so they could use different size of tile size, but we can see Stream-K advantage already here, particularly for a smaller size part as well. That's pretty much for my summary for the current Triton implementation of Stream-K. Thank you.
Thanks, Xiao. Are there any questions for the AMD team? Go ahead. Yeah.
Yes, I'm curious. In this last results, like which you mentioned, there are multiple kernels you wrote, right? Which one is that using in this case?
You mean a blue point or you mean the red point?
Yeah, the blue points.
So blue points, I've actually not multiple results. So I only use the tile size 64, so I only have one configuration.
But you mentioned a bunch of kernels, right? Like earlier in your slides, there were like 2 kernel solution, like 1 kernel with.
I see. Here's the latest. We have like 1 kernel solutions for that, but I use atomics. Sorry for that. Yeah.
With atomics. Okay.
Yeah,
okay.
It's
and
atomics.
that's expected to be the best one?
No, definitely not. Because we think atomics actually going to slow down. So we actually want to have non-atomic approach. So there's ongoing work going on at the moment. Yeah.
Interesting. And do you have sorry, one more question. Do you have reference kernels written in like ROCm or something like that already?
What do you mean reference kernel?
Meaning non-Triton kernels, like written in just C++, right?
So here the speed up we compared with Triton. PyTorch Matmore. Underline it use Rock Blast basically.
Yeah, but we do like we do have kernels that are non-Triton for Stream-K though. At AMD.
Okay.
Yeah, so.
Yeah. Oh, that means yes. We have a heap implementation for that. Yeah.
Right. Oh, yeah, that's what I was wondering. So I'm getting confused with the different terms. And in the heap implementation, the best one is actually the one without atomic, the single kernel without atomic.
So in the heap implementation, they have both. So both partial sum with multi-buffer methods to replace atomics. Yes, have both methods there.
Okay, and it just there's not one strictly better than the other, I guess.
I think as far as I know, I think I was told they prefer multi-buffer methods to replace the atomics. That's what they're doing at the moment.
Okay. Okay. Super interesting. Yeah. Thank you.
Yeah.
Yeah. Thank you. Any other questions or any other comments in general? Okay. If not, thank you, everyone. I'll post the minutes and the recording soon. Thank you.
Thank you.
Thanks all.
Thank you. Bye.